This conference will now be recorded.
Hello everyone. So we are starting with methods of purification of organic compounds. We are continuing in this topic for the last 2 classes or 2 to 3 classes, and under which some of the part we have already covered and some of the part is left under this heading. So once these methods of purification of organic compounds are finished, next we'll discuss some problems, and after that we will start qualitative analysis for organic compounds. Okay. So under this heading of methods of purification of organic compounds, we just have a initial idea about thin layer chromatography in the last class. So thin layer chromatography, it is a type of adsorption chromatography. So under adsorption chromatography, we have already covered the column chromatography, and the second type under the adsorption chromatography is thin layer chromatography. Okay. So initial idea we have already seen, and today we will just try to understand that how it looks, that how the process is done. So the main difference with column chromatography is that in this case minute quantities of mixture we can separate, and this is very ideal for this small quantity of compounds. If we have large quantity of compounds, column is better, but for little amount of compounds of mixtures that we want to purify, this method is better. So in this case, there will be a sheet of glass. It may be a plastic or aluminum foil. And on this sheet, there will be a thin layer of adsorbent. So that is what is adsorption chromatography. And this adsorbent is either silica gel or alumina. Remember, in case of column chromatography, inside the column, we fill it with silica gel or alumina. But now we are not using column, but we are using some sheet made of glass, plastic or aluminum foil, and on the sheet there is some layer, thin layer of this absorbent, and that is why this chromatography we are calling it as thin layer chromatography. It is called chromatoplate or thin layer chromatography plate. Now once the plate is made, sometimes it is also commercially available. So the next thing that we do, we put a drop of the mixture, that is the compound that we want to purify, just above one edge, and the plate is then placed in a closed jar containing eluent. Eluent is nothing but solvent. Now this may be a single solvent or it may be a mixture of solvent. So here you can see in this picture, we have taken this plate in a beaker and there is a little amount of solvent, and the spot, that is a sample spot, the compound that we want to purify, or you can not just purification, you can also understand whether, that is, how many components are present, how many compounds are present in the mixture. That idea also we can get from this chromatography. So here this spot is given at this position, and one thing that we have to be careful, when we are dipping this plate in the solvent, this solvent layer, it must be below the mark of the spot. That is, suppose if the sample we are dipping it like this and you are giving the spot here, it is completely wrong. The spot should be above the layer of the solvent. Fine. So here the solvent, that is the starting point, that when the solvent will be eluting throughout the plate. Okay. So now in the step 2, gradually when the solvent is eluting through the plate, in case of column we have seen it is towards gravity, but now it is anti-gravity movement. Fine. And now we are seeing some color separation. There is component A and component B with two different colors, and when they are combined together it looks like this, but gradually now you'll be able to understand the separation. So in this case, for simplicity, we have just taken 2 components, but it is not necessary, it may be more than 2 components. Okay. So in the second step, this is the picture, and in the third step, that is, the more is the time will be, that is, with increase in time, this separation between these 2 spots, or if it is more than 2 spots, that is also another possibility, but the gap between the spot, now it will increase. So in this case, the gap between this blue spot and red spot, and here the gap is gradually increasing, and maybe with more time lapse, the gap, it may be even increased like this. Okay. So in this way we can separate it. Now depending on the size of the plate or the amount of compound you are purifying. And suppose this is a desert compound and red one is the impurity. That is one possibility. In this case, we will say that we are doing purification. But suppose both are required, then we can say it is a separation of these two compounds. And whatever it is, whether this is both the spots are desert or only one of them is desert, next what we can do, in this spot, we can scratch the adsorbent and we can dissolve it in some solvent. So the compound will be soluble in the solvent and the adsorbent that will be in the form of precipitation and we can filter it out. So in this way, we can separate it. And if our purpose is just to check whether there is any mixture present in the sample, then that we can easily from the visual observation we can understand. But if our purpose is to purify it, to separate it, suppose there is some 100 milligram of mixture and among this you want only this blue part, you want only the component A. So once the process is done, that is solvent will reach somewhere at this point, that is the other terminal of this plate. Then what we will do, this portion where the desert spot is present, you will just scratch the part of the adsorbent and then with some suitable solvent in which the compound is soluble, we can separate it. Okay, so this is the principle of thin layer chromatography. Now, related to thin layer chromatography, there is one important term that we have to learn, and that is known as RF factor. So in the next slide, we will see what is RF factor or RF value. Actually, it is also called retention factor. So when these components of the mixture, they are moving up along with the eluent to different distances. We have already seen that the blue one, it is moving that is higher, its position is higher compared to the red one, right? So there is different types of movement and that is the speed of movement is different. So the components of the mixture move up along with the eluent, that is the solvent or mixture of solvent, to different distances, and that depends on the nature of the compound, depending on their polarity. More polarities, the less distance it will travel. Remember, in case of column chromatography also we have seen the more polarity, the more time it will take for elution. So there will be different movement to different distances, and that is depending upon the degree of absorption. So when polarity is very high, the degree of absorption that is also very high. And from RF value, we will be having some, we can get the idea about their degree of absorption or degree of movement. So here in this picture, you can see this is our starting point where the sample spot is there. And just for simplicity here, we have taken as if it is a single compound. Now, when after elution of the solvent, suppose this is the solvent front. So this is the starting point, that is origin. And this is the point where the solvent moved up to this point. So the process should be, experiment should be done in such a way that when it is reaching somewhere here, that is almost at the end, it should not be at the terminal, it should not touch the terminal position of the plate, it should be somewhere here. Okay, it may be 1 centimeter or 0.5 centimeter like this. So when it is touching somewhere here, so this is actually the distance for the total solvent movement, and that distance is 2.8 centimeter. Okay, so the solvent movement started here and ended here. So this is the total distance for the solvent movement, and the total distance for the movement of the spot or any compound. So here only one spot you can see, which is moving from, this is the origin, because origin is always you have to consider it same, whether it is solvent or the spot. So this is the starting point for both of them. But the position of, that is after elution of the solvent, the position is here and the value we are getting 2.1 centimeter. So this 2.1 centimeter, if you are dividing it by this total distance of the solvent, we are getting the value 0.75. Similarly, suppose there is another spot which is somewhere here, and you have to now measure the distance. So this distance is, suppose it is 1.9, just for arbitrarily I am saying 1.9. So the RF value for this red spot, that should be 1.9 divided by 2.8, and obviously that value will be lesser. So from the RF value 0.75 for the blue spot, and for the red spot it will be something some lesser than this, because it is now 1.9 divided by 2.8. Okay, so when RF value is less, that means its movement compared to the other compound where RF value is high, it is less, so its movement is less. So RF value in this way, it will give us some information regarding the degree of absorption of different components. Okay, now the next thing is, sometimes we have to do detection of spot in the thin layer chromatography. Now if the spots are already colored, if it is colored compound, without any assistance of, without doing anything else, you can easily all the spots are visible to you, right? Because they are already having some colors. So spots are already visible in TLC plate, but that will not happen always. So sometimes there may be some cases where the compounds are colorless. So what you will do? So when the compounds are colorless, there are actually three things that we normally do. First of all, if the compound fluoresces in UV light, then we can take the help of UV light for their detection. So in this way, what happens? Normally UV light, if you consider its wavelength, it is lesser than the visible spectrum, that is the electromagnetic spectrum, the portion which is visible. If you consider the wavelength, and the UV ultraviolet light, if you consider the wavelength, obviously now it is shorter wavelength. So that is not in the visible part. But sometimes what happens, UV light are absorbed by some organic compounds, not just organic compounds, but here I am just using organic compounds term because we are talking about purification of organic compounds. So when UV light absorbed by some organic compounds are reflected back as longer lambda value, then you can see the spot as visible radiation. So what happens? We just, after the TLC is finished, if it is having some that type of property, then under UV light we can see the spots in this way. So see, under UV light the spots are, they are having some purple color. So if it is having this type of color, so when you will remove the UV light, it seems as if it is a white TLC plate. You will not be able to see any color. But when you are putting it under UV light, if there is this type of fluorescence property in ultraviolet light, then you will be able to see the spot. So this is one way you can detect the colorless compounds. The second method is, the plate can be placed in a covered jar, that is closed jar basically, where there is some few crystals present. And what will happen, some compounds there is a tendency to absorb this iodine vapor and they will appear as brown spot. Now directly crystals of iodines are not taken. What we do in that closed jar, we take some silica gel, the same thing that we have used in column chromatography. So in the silica gel we put some iodine crystal and the compound is dipped in that. So you can see here we have some silica gel, it just look like sand. Okay, so here we have some iodine crystals already present, so that is why the silica gel, it appears as brown, though actually silica gel is white, but it appears here as brown because already there is some iodine crystals, iodine solid. So in this closed jar, when we are putting the TLC plate and keep it for some time, 1 minute or 30 seconds, you will be able to see this type of spot. And when we will bring this paper out of this jar, then with time this vapor will be evaporated and you will not be able to see any spot. But again, if you put it in the closed jar containing iodine, you will be able to see brown spot. But that is, it is not that you will always get it. It may happen for some compound. So this is another way, second method by which you can detect spot in TLC. And the third method, that is specially for amino acid. So amino acid, we know the general formula is, if it is carbon, there will be some R group, and with this carbon there is H, there is NH2 group, and there is CO2H. This is basically alpha amino acid. So for alpha amino acid, what we do, If you have some mixtures of amino acid like this, alpha amino acid, suppose 2 to 3 amino acids you have, and then you have done the TLC plate. Now the spots are colorless, you cannot see it, but we can spray some neem hydrogen solution. Okay, so details of this you will study in specific chapter for amino acid, not here. But neem hydrogen is a compound which, when in presence of amino acid, it forms some complex, and the complex with this amino acid, they have some specific color, mostly towards red side. It may be pink or magenta or red, something like this, but there will be some difference in the color. So amino acid can be detected by spraying the neem hydrogen solution over it. Then there will be some intense color formation, mostly in the pink, magenta, red related color. Okay, so these are the different ways by which we can detect if we are using colorless compounds. And if it is already having color, we don't have to use any other iodine or UV light or neem hydrogen solution. Okay. Now partition chromatography. So we have already covered adsorption chromatography, under which we have seen column chromatography and thin layer chromatography. Now for partition chromatography, the main difference with adsorption chromatography is that in this case, both the mobile phase as well as stationary phase, both are liquids. In case of adsorption chromatography, you have seen that stationary phase is solid, which is basically this absorbent, solid absorbent, silica gel, it may be alumina, and mobile phase is liquid. But now, when it is partition chromatography, both the phases are liquid. That is the difference with adsorption chromatography. And under this partition chromatography, we will just study paper chromatography. Now, at a first glance, paper chromatography and TLC, they will appear to you as same. But don't be confused, these two are not same. Paper chromatography, the principle is partition chromatography, where both mobile as well as stationary phase, both are liquid. But TLC is not under partition, that is for under adsorption chromatography. So in paper chromatography, it is basically almost the same procedure as we follow in TLC. Now the difference is that in case of TLC, what you have done, you have taken some glass plate or aluminium foil or plastic plate over which there is some thin layer of solid adsorbent. But now there will be some special paper, special strip of paper. Why I am saying special paper? It is not just any paper over which we write. No, it is not that kind of paper. It is chromatographic paper, and this is made of cellulose. Okay, and these are easily available. So in this paper chromatography, which looks like TLC, but actually it is a specially made from cellulose, specially made paper, which is used for paper chromatography. Now, if it is paper, then how this stationary phase is liquid? That question may arise. So what happens? Here the stationary phase is water molecule absorbed, or you can say trapped between the cellulose fibers of the paper. So when you will touch the paper, obviously you will not be able to you will not feel it as wet. It will appear dry to you. But that doesn't mean there is no water stationary phase. There is already some water trapped between the cellulose fibers of the paper. So the paper itself is not the stationary phase. The water trapped between the fibers of the paper, that is actually the stationary phase. And solvent or mixture of solvent is the mobile phase, just like you have seen in case of TLC. So see, it looks like TLC, but be very careful. It is not TLC. It is a specially made of from cellulose, special type of paper where stationary phase is already trapped, which is nothing but water. So we have placed the solvent, the spot of the sample here. That is the origin of the spot. Now you have dipped it in some solvent. So this is the solvent on mobile phase, this part. And this is the paper where already the stationary phase is present, which is water. Now with increase in time, as time lapse is there, what will happen? There will be this spot will be separated in different components depending on how many components are there. So the solvent will start from here and it will reach at this point. And you can see here we have different types of spots. So from this distance, you can again take the RF value, just you have taken it in case of RF. Same method. Okay. Now we will solve some question, and that is based on until now we have studied different types of purification methods. Remember, there is crystallization, sublimation, distillation. So based on that, we have question here. In the left hand side column, we have some mixture of compounds, and in the right hand side column, we have different types of purification methods. So we have to match it. We have to find the correct match. Chloroform and aniline, now both are liquid, and we when we try to understand the distillation, what type of distillation, vacuum, simple or steam, we have to have some basic idea about the boiling point, whether the boiling points are close to each other or they are highly different from each other. So from chloroform it is around 61 degrees centigrade, and for aniline it is around 184 degrees centigrade. So you can understand huge difference is present, right? So we can easily apply simple distillation. We don't have to do any special distillation. Then we have orthonitrophenol and paranitrophenol. Now this particular example I have already discussed when we have studied steam distillation. So in orthonitrophenol, OH and NO2 group, these are close to each other in this case. But when it is paranitrophenol, they are far from each other, right? So intramolecular hydrogen bonding, that is possible only in case of ortho, not in case of para. And this intramolecular hydrogen bonding is like this. So because of this, what will happen? Every molecule of orthonitrophenol, they will be they will not link to each other. But when it is paranitrophenol, this OH group, it can make hydrogen bond with another paranitrophenol, where NO2 group is in this side. Suppose now if you are drawing the molecule while keeping the NO2 group in this side, right? So now there is hydrogen bonding possible. So in this way, what is happening? There is intermolecular hydrogen bond. And in this case, there is intra. Within the same molecule, you have hydrogen bonding. So each molecule is individual. So you can easily separate them. Now what is happening? Because of this special property, only the ortho nitrophenol is steam volatile, not paranitrophenol. It is having very high BP and MP, melting point boiling. Now as this one is only steam volatile, when you are applying steam distillation, this only the orthonitrophenol will be mixed with water and it will be collected in the that is in the distillate part, and paranitrophenol that will be remaining in the distillation flask. That means steam distillation, C is matching with 2, 2 is matching with C, 1 is matching with D. So first one is D, second one is C. It is matching with last option, isn't it? Next is hydrogen peroxide and water, and then we have benzoic acid and naphthalene. Now hydrogen peroxide and water both are liquid. Benzoic acid and naphthalene both are solid. That means when both are solid, there may be sublimation or crystallization, but in the options we don't have sublimation, and that we only have crystallization here. Now naphthalene and benzoic acid, between these two, though both are organic compound, but remember naphthalene is simply hydrocarbon. It is non-polar. But when it is benzoic acid, there is CO2H group present. So it will be more polar. So it will have some solubility in hot water, unlike naphthalene. It is more having more non-polar nature. So because of this difference in solubility, we can apply crystallization. So 4 will be matching with A, and only one option is left, which is vacuum distillation, that is for hydrogen peroxide. Now if we summarize all the points, chloroform and aniline, they are mixture of liquid and their difference in boiling point even greater than 40 degree. Basically, if it is greater than 25, then also you can apply it. But here it is even greater than 40 degree. Simple distillation is enough. Then orthonitrophenol is steam volatile, but paranitrophenol is not. So we will utilize this fact. We can separate them by steam distillation. H2O2 decomposes even before reaching its boiling point. So we know when we have very sensitive compound which just before its boiling point there is a chance of decomposition, or for very high boiling point compound we can use vacuum distillation. So these are the situation where we use vacuum distillation. So in this case we will use vacuum distillation, or you can say distillation under reduced pressure. And the last one, both benzoic acid and naphthalene undergo sublimation. Though in that column 2 we do not have any mention of sublimation, but this information is important because when both are undergoing sublimation, suppose in column 2 you have sublimation, so just for information it is important for us to know that both undergo sublimation, so we cannot use this method. And regarding crystallization, we can say benzoic acid is soluble in hot water but not naphthalene, and that is the result. That is the reason you can use simply hot water for their crystallization. So when you will dissolve it, this part will not be dissolved, so you can separate it by filtration, and whatever is left in the water, by evaporation of water, we can get the crystals of benzoic acid. So that is why 4 is matching with A. So 1 is D, 2 C. It is basically the last option. Okay. Now the next question is also list matching type of question, and some of the options you will also get same, but some options are also different. Again we have chloroform and aniline, and we know we have to do here simple distillation. So A is basically matching with 3. Though here nothing, simply distillation is mentioned, so it means actually simple distillation. Then benzoic acid naphthalene, we have already seen it that we have to do it crystallization. So B is matching with 4 basically, right? And C, in the previous problem I have already said that sublimation you can't do for sublimation method, you cannot use for these two compounds because sublimation will happen for both. Okay, so here sublimation option is given, but this is not for benzoic acid or naphthalene. You have to do crystallization, and the reason we have already seen in the last problem. Then we have again two mixtures of solid, both are solid, naphthalene and sodium chloride. Now you know that sodium chloride is inorganic compound. Naphthalene is sublimable. So for this mixture of two solid, you can simply use sublimation because only naphthalene will be sublimed, not sodium chloride. So D should be matching with 2. So D is matching with 2, A is matching with 3, right? Then B is matching with crystallization that we have already seen. Only one is left, C. And which one is left? It is steam distillation. Now the question is water and aniline, how steam distillation is possible? Now aniline, it is 184 degrees centigrade, which is far greater than water. But what happens when water and aniline we have mixture? It forms azeotrope, and azeotrope is some solution when you are mixing two liquids. Suppose you have mixed liquid 1 with liquid 2. Now individually, if you consider their boiling point, and if they are forming some azeotrope, the new boiling point that is lesser than both of these. So what happens in case of water and aniline? When they form azeotrope, the new temperature, the new boiling point that we get is 98 degrees centigrade, which is lesser than water. Now what happens if you have some impurity mixed with aniline? Then suppose you have some, though here impurity is not mentioned, simply water and aniline is mentioned, but basically when we are saying purification, suppose there is some impurity mixed. I am writing I for impurity. Now if you want to purify aniline, what you will do? You can do steam distillation, because only aniline will form azeotrope with the water. It will have some boiling point near about 98 degrees centigrade, and it will be coming in the distillation, sorry, in the distillate part. That is after distillation, whatever we get. And you will get some mixture of aniline and water. Now in this aniline and water, they will form some immiscible layer. You can easily separate them in separating funnel. But impurity in this way we can remove from aniline, And here these, because as they are forming some azeotrope, so that is why steam distillation we can use for water and aniline. Though aniline is having very high boiling point, but steam, it will be steam volatile, because the condition for steam distillation is that the compound that you are trying to purify, that must be steam volatile. That is the criteria. So aniline is already fulfilling that criteria, so that is why you can use steam distillation for purification of aniline. So C is 1. So this is our answer, A3B4C1D2. We'll go to next question. Here we have a figure, and this is column chromatography figure where 3 bands are given, A, B, C. From the figure of column chromatography, you have to identify the incorrect statement. There are total 4 statements, A, B, C, D. The first statement is saying that compound C is more polar than A and B. Now C is coming at first. So when you are eluting, C will be coming first, right? Then B, then A. So how C is more polar? So polarity order, if you consider here, A is maximum polar, because after C is eluting, next B will be eluting and then A. So polarity order is like this. So C is more polar than A and B. It cannot be correct. It is incorrect. Incorrect, right? Then compound A is least polar. This is also incorrect, because A is maximum polar. It is not least polar. Then compound B, that is C. Okay, one thing just notice that we already know A and B both are false. Now A and B together you can find in option 1 and in option 3. That means these two you can cancel. Okay, now C, third statement is saying compound B comes out of the column before C and after A. Now it is true they will be coming after A, because that is the polarity order. Sorry, what it is saying, that compound B comes out of the column before C. No, it will not be coming before C. C will be coming first. Second position is for B and then A. So it will be coming before C after column. That is not correct. The correct statement should be it will be coming out after C and before A. So if you change this before to after and after to before, then it is correct. So C is actually not correct. So all the 3 statements you can get only in option 1. But why D is correct? Compound A spends more time in the column, and that is true, because this is maximum polar. So obviously it will spend maximum time in the column. It will come at last point, already when you have already have B and C out of the column. So D is basically correct statement. It is not incorrect statement. So A, B, C, that is option 1 should be the correct option, right? Here we have again chromatography related question, and this is basically RF value related question, right? Following chromatogram was developed by adsorption of compound A on a 6 centimeter TLC glass plate. So this is TLC, already mentioned. Total distance for the glass plate is 6. Total distance means this total distance. This is 6 centimeter. Retardation factor of the compound A in this format you have to find. Now total distance is 6 centimeter. So when you will try to find RF value, what you will do? First you need the distance covered by the compound, and that distance is mentioned 3.5. But you have to start, that is the distance should be from this point up to this point. So you need basically this distance. Now it is not 3.5. 3.5 is considering this part also. So you have to subtract. So RF value, it should be, that is denominator numerator, if you consider it should be 3.5 minus 0.5. And what is the distance by the solvent front? By the solvent front is totally 6. But these two part, this distance and this distance, that you have to subtract. But because we need only this part, that means 6 minus 0.5. again 0.5. Now the value will give you RF, which is basically 3 by 5. This will be the RF value. So see here the RF value, distance moved by the substance from the baseline, which is 3 centimeter. How you are getting is 3.5 minus 0.5. Then in the denominator, distance moved by the solvent from the baseline, and that distance is basically 5. But how you are getting it? 6 minus 0.5 minus 0.5. So ultimately you are getting the ratio 0.6, but you have to write it in this format because that is the format given in the question. But your answer will be 6, integer type of question. 6 into 10 to the power minus 1 means it is actually 0.6. So 0.6 is the RF value, but fill in the gap, that value will be 6. So we have finished the purification part of organic compounds. Next we are starting qualitative analysis of organic compounds. Now what is qualitative analysis? That we have to understand, because qualitative analysis and quantitative analysis, these two are not same thing. Now from the term itself you can understand, when we are talking about qualitative, we are just trying to find out the different elements present. We are not interested in its amount. We just want to know whether it is present or not. So qualitative analysis involves detection of different elements. It may be carbon, hydrogen, oxygen. Mostly we'll also see what are the elements. Mainly carbon, hydrogen, not the gaseous elements mainly, that is carbon, hydrogen, nitrogen, all these elements in a given organic compound. Actually, it is also true for gaseous. It is by mistake I have said that it is not for gaseous, but it is also possible for gaseous. Okay. So here qualitative analysis involves different element detection, that is whether they are present or not, that is yes or no. Now qualitative analysis is focused on finding the elements and the ions present. So sometimes it's not just element, it may be the presence of ions also. For example, suppose if we are trying to find whether there is any halide ion present, that is whether Cl minus ion is present, that also we can find. Or if we are say finding the elements, that is whether there is presence of nitrogen as element that is present or not, that also we want to we will be able to analyze when it is qualitative analysis. So here we are not finding any actual amount, we are just trying to find whether it is present or not. Now which elements will give priority? Carbon, hydrogen, oxygen, nitrogen, then phosphorus, sulfur, halogens. Okay. So next, so we'll start with detection of carbon and hydrogen. Now we are talking about organic compounds. Now when it is organic compounds, obviously carbon will be present. Right? So still why we are talking about detection of carbon. So basically the test that we are going to study, that is performed only to establish whether a given compound is organic or not. Because so this, the purpose here is just to know whether it is organic or inorganic. Because if it is organic, always carbon will be there. You don't have to test it. But if you want to know whether it is organic or inorganic, then you have to do this test. With the exception of few compounds. So these are considered as organic compounds. But see, in these compounds, you do not have any hydrogen. Though most of the organic compounds, there is presence of hydrogen. But these are especially some examples where you cannot find any hydrogen. So except these few compounds, all organic compounds also contain hydrogen. So carbon and hydrogen, these two are such elements when that is, these two are such elements which will be always present in organic compounds, except these few cases. Fine. So what we do in this case, how we do the experiment, how we detect carbon and hydrogen present or not. By heating the compound with dry copper 2 oxide. Now copper oxide. Copper can have two different types of oxidation state. It may be copper +1 or +2. So here you can see it is +2. So the formula is CuO. Because for oxygen, the oxidation state is 2 negative. That means it must be 2 plus. So we have to take CuO. If I am saying it is copper 1 oxide, then the formula will be different. Then it will be Cu2O. Now the oxidation state is +1. But we are not talking about it. We are talking about this CuO. So this CuO, when we are heating the compound, if carbon is present, that means if it is organic compound, this carbon, it will react with CuO and it will form carbon dioxide. And copper will be now copper oxide, it will be converted to metallic copper. What about hydrogen? If hydrogen is present, it will also react with CuO, it will form H2 and metallic copper. So similar type of these two equations, there is some similarity because from carbon you are getting its oxide, from hydrogen also you are getting its oxide, which is simply water. So these two are the reaction that will occur if carbon and hydrogen, these two elements are present. Fine. Now the next question is how to know whether carbon dioxide is generated or water molecule is generated. That you can understand by doing this test. We know that carbon dioxide, it has this property, it can convert lime water milky. Lime water is CaOH whole to solution, calcium hydroxide solution. So the CO2 gas, that is when you are doing the experiment, the gas that will be generated, if you are passing it through calcium oxide hydroxide solution, and if the calcium hydroxide solution is turning milky because of the formation of CaCO3, that will prove the presence of carbon dioxide generation. And similarly, how to know whether water is present or not? How we will prove water is generated? What will happen? The condensed water vapor that will be generated, actually here water vapor will be present because you are heating the mixture with CuO, and under that condition H2O will be in the vapor form. So this water vapor, it has also another property. If you have anhydrous copper sulfate, which is basically white, but in presence of water vapor, it turns blue because of formation of CuSO4 5H2O, 5 water molecules of crystallization. So because of these two conformation test, you can be confirmed whether CO2 is generated, because CO2, there is no smell, there is no color, it is colorless, odorless. So you have to be confirmed whether it is generated or not. Similarly, water vapor also we have to be confirmed, and that we can do by using anhydrous copper sulfate, because if it is converted to blue color, that means water vapor is present, and the source of this water vapor is, that is a hydrogen source, is the organic compound that you have used as sample. So here you can see the picture for this experiment. So what we have done here, in this case we have taken this organic compound with CuO, and here the ratio is almost 1:3. Now 1 is for organic compound and 3 is for CuO. So you have mixed these two together and you are heating it very strongly with this 3 times CuO powder, copper oxide powder, you are heating it strongly. Now if there is presence of carbon or hydrogen, what will happen? There will be generation of CO2 and H2O. Now in this bulb, you can see we have taken some anhydrous CuSO4, which is normally white. But if water vapor is coming in contact with this, after some time it will be converted. That is, after this heating process, you will see this is converted to blue color. If it is not converted, that proves hydrogen is not present. But if it is converted to blue color, that means what hydrogen is present. And in presence of CuO, remember the reaction 2H. In presence of CuO, it will produce H2O and copper metal. So this will be converted to blue color. And the CO2 is also there. It will be coming in contact with lime water, which is solution of CaOH whole 2. And when CO2 is in contact with this calcium hydroxide, At the first, that is before CO2 is coming in contact with this, it is transparent, clear. But when it is coming in contact with CO2, it will turn milky appear. There will be some milky appearance because of formation of CaCO3. So in this way, we can, this is the procedure and the experimental picture you can see here, from which it is clear how we can do the test. Fine. Now there is a modified procedure. If when we'll use the modified procedure, in case the compound is not solid. So in the previous case, you have seen the compound is solid, you have mixed with this solid 3 times UO powder, you are heating it strongly in hard glass test tube. But that will not do if the compound is liquid or gas. So this is the case when you have to use modified procedure. Another thing is, if sulfur is also present in the organic compound, then also you have to use this modified procedure. So what is this modified procedure? How it is different from the previous one? In the previous one you have seen we have just mixed it with 3 times CO powder, we are heating it strongly in hard gas test tube, but now that is not the case because the organic substance, it is either volatile liquid or gas. So what you will do, it is already in vapor form. The vapor of the organic compound, we will directly pass it through the heated CuO. Directly we will not mix it with CuO or heat it, but we are passing the vapor because it is already in vapor form through heated CuO, which is taken in hot glass test tube, and the gases that will be evolved. If carbon hydrogen patient, then which gases will be coming out? H2O vapor and CO2. So they will be tested as these two that you have already seen how we have done it using copper sulfate for detection of H2O present or not, and use of calcium hydroxide solution, which is lime water solution, for detection of CO2 as usual. Only difference, you are not directly mixing the compound with CuO because that is not possible. Now it is not solid, now it is liquid or gas. Now if sulfur is present, if the organic compound also contains sulfur, what happens? There is something will happen which is just like this, that is the observation is just like CO2. So what happens? This sulfur is oxidized to SO2 in presence of CuO. In presence of CuO, sulfur is oxidized to SO2 and CuO is converted to cuprous oxide. Now this SO2 is having the same type of property just like CO2. This can also convert clear solution of calcium hydroxide to milky appearance, calcium sulfide. This is also having some milky appearance just like CaCO3. Similar observation. So if sulfur is present and you are seeing milky appearance when it is passing through CaOH2 solution, you will draw the conclusion that okay, CO2 is coming out, so carbon is present, but that is not the case. It is same type of observation when S is present. So formation of insoluble calcium sulfide, just like calcium carbonate, in both cases same type of observation. So what is the solution? If this type of situation arises, what we will do? So what we do, if sulfur is present, you already know it, the evolved gases, that is the whether it is CO2, H2O, SO2, whatever, SO2 must be there because we are talking about the situation where sulfur is present. So the evolved gases, you have to pass it through acidified solution of potassium dichromate, K2Cr2O7. Now, if this compound has this property of absorbing SO2 under acidic condition, so when it absorbs SO2, it converts it to Cr2SO4, which is having green color. So because of this type of reaction, now SO2 is no longer present. It is already converted to chromic sulfate. It will turn it to green chromic sulfate. Now once you have done this, now the SO2 is already removed. After this, the gases, whatever gases are left, you can pass it through lime water as usual. So after doing this, you are passing it through calcium hydroxide solution, that is lime water. And if you are seeing that still there is some milky appearance, that means CO2 is present because you have already removed SO2. by this reaction by using K2Cr2O7. Still you are seeing milky appearance when you are passing it through lime water. Why it is happening? Because CO2 is present, right? But if you are not seeing it, that means CO2 is not present because you have already removed SO2. So there will not be the same observation expected from SO2. Okay. So this is a modified procedure. If it is not solid, then you have to apply the first method. And if sulfur is present, then you have to do this extra step. Extra step means this reaction you have to do. Just remove SO2, then do the test as usual for carbon and hydrogen. Okay. So detection of carbon and hydrogen we have seen. Next is three elements detection we will study together. And why together? Because there is a common test for these three: nitrogen, halogen, sulfur, and that is Lasagne test. Okay. So in this test, the covalently bonded nitrogen, sulfur, halogen. Covalently bonded means because we are talking about organic compounds. So if there is presence of nitrogen and sulfur, obviously that will be covalently bonded. So one example I can give you. So nitrogen. So if you have taken suppose pyridine. So here we have this organic compound. So nitrogen is present. Then if we have thiophene, this is called thiophene. So in this case also sulfur is present. Then halogen. Suppose we have CH3, CH2Br. So here halogen is present. So these are the different cases. Though this compound it is not solid. So mostly it is for solid or liquid because handling gaseous molecules it is difficult. So for this test mostly it is liquid or solid. So these are some examples where halogen, nitrogen, sulfur present in organic compound. So what we have to do in this test, what we do actually, we convert all these elements, nitrogen, sulfur, halogen, to the corresponding water soluble ions in the form of sodium salt. So as if this covalently bonded nitrogen, sulfur, halogen that is present in organic compounds, in this test we convert them to some compound with sodium, as if now you have some inorganic compound. They are converted to sodium salt. That means in this test you have to use some sodium. So what we do a fusion test with sodium metal. So directly we use sodium metal. Now in this test we will obviously see the procedure, but I'm just discussing the principle. So in this test what we do, after the fusion we get some extract which is called Lasagne extract. Now this extract is used to detect ultimately the presence of these elements in the organic compound. And this extract is nothing but it is containing all the sodium salts of these ions. Fine. So how we will do this test? This test is nothing but preparation of this extract. First we take a small piece of sodium metal. Normally sodium metal it is very reactive. You cannot keep it in open. It is kept under kerosene oil. So you have to take one small sodium piece. You have to dry it because it is already in some oil, kerosene oil, where it will be in inactive form because you can't keep it in open air. Alright, because it is very reactive alkali metal. So you have to dry it by pressing between the folds of a filter paper, and then you take it in a fusion tube and you have to gently heat it because it is already reacting. Gently heating is enough. So when it is in contact with some gentle heat, it converts to shiny globule. So first it is in solid form, there is some shiny appearance but not so shiny. But if it is contact with a little amount of heat, it will be converted to some shiny globule. Now the tube is removed from the flame and you have to add a pinch of organic compound, not much, very little amount is added to the test tube and heated strongly. Now this tube is specially designed tube which we can break easily because ultimately you have to break this tube. So when it is organic compound is added which you are trying to analyze, whether N, S or halogen present. So you have to now heat it till it becomes red hot. So it must be red hot. Once it is red hot, now you have to plunge it in some china dish which is already containing some distilled water. So you have to plunge it means you have to break the portion where this mixture of sodium and organic compound is present. Now look at this picture, it will be clear how everything will happen. So we have taken sodium and organic sample after this shiny globule formation. So this is the ignition tube. You have to hold it with this test tube holder. And sodium and organic sample is heated up to it is red hot. Once it is red hot, then you have to take it in some china dish. You have to plunge it. Red hot ignition tube is plunged in 10 to 15 ml distilled water, which you have already taken in this type of design dish called china dish. Now you have to boil it and reduce the volume to some extent. Boil for a few minutes, then you cool it and you have to filter it because there is also already some broken part of glass, some impurity may be there. So just take, you have to do the filtration and you get this clear sodium extract. And this extract you have to use for all the tests related to nitrogen, sulfur and halogen. And this filtrate, we call it fusion extract or lasagne extract. So there are different names that we use for this extract. So the purpose of this test is to make the sodium fusion extract where all this NS halogen, they are present in the corresponding water soluble ion in the form of sodium salt. Fine. So just have a look here. Sodium with when it will react with carbon and nitrogen, because carbon is always there, it is organic compound, it will be converted to NaCN. So this is as if sodium salt of cyanonegative cyanoion, right? So now the nitrogen is part of the anion. So when nitrogen is present, you will get sodium cyanide. Similarly, when sulfur is present, you are getting another salt of with sodium. Here sulfur is basically sulfide ion. So all the elements now they are in ion form. And suppose both N and S present, now you will have this ion which is SCN minus. It is making salt with Na plus. And if halogen NaH, suppose Cl, then there will be formation of NaCl. So these are the different possibilities depending on what elements you actually have in the organic compound. So C will always be there. The first equation if only N is present, second equation if sulfur is present, third equation if both N and S present and you are using insufficient amount of sodium, you will get this type of NaSCN salt, sodium thiocyanate. And if halogen present, where X is Cl, Br or I, you will get NaX. So details of this we'll discuss in the next class. We're ending the session here. Thank you for listening.